Suppose you get up in the morning and look out at your car. One of two things is true. Either your car has a flat tire or it doesn't. The probability of it having a flat tire is 1%. The probability of it not having a flat tire is 99%. Suppose you do this 2 days in a row. The probability of your car not having a flat tire on both days is 99% times 99%, or 98%. And if you do the same thing 4 days in a row, the probability of you not having a flat tire on any of those 4 days is 99% times 99% times 99% times 99%, or 96%. And if you look out at your car each day over the course of 16 days, the probability of you not having a flat tire on any of those days is 99% raised to the 16th power, or 85%. This process is called a binomial distribution. You have a binomial distribution when there are a number of trials, and among those trials you're looking for a number of successes, and each success has the same probability of occurring. For example, each day you got up is another trial. It's an opportunity for you to observe either a flat tire or not a flat tire. A success is observing no flat tire, and the probability of a single success is 99%. Now, it's easy to calculate the probability of not getting any flat tires over 16 days. That's 99% to the 16th power. It's also easy to calculate the probability of getting a flat tire on every one of the 16 days. That's 1% to the 16th power, or virtually zero. It becomes difficult to calculate the probability of a number of successes in between either zero or all of them. For example, suppose you buy an orange. The probability of the orange going bad within 24 hours is 10%. So the probability of the orange not going bad within 24 hours is 90%. Now suppose you buy 2 oranges and you want to know what is the probability of neither of the oranges going bad within the next 24 hours. This is a binomial distribution. You have 2 trials, that's each of the oranges. You're looking for no successes, that is, we want neither of the oranges to go bad. And we know the probability of a single success, the probability of an orange going bad within 24 hours is 10%. So the probability of no oranges going bad is 90% times 90%, or 81%. Similarly, it's easy to calculate the probability of both of the oranges going bad. The probability of one orange going bad is 10%. The probability of both oranges going bad is 10% times 10%, or 1%. Now, what is the probability of only one orange going bad? Well, notice this becomes a little more complicated because the first orange could go bad, but not the second one. And the probability of that happening is 10% times 90%, or 9%. But also, the first orange could not go bad, but the second one does go bad. The probability of that happening is 90% times 1%, or 9%. So notice, with just 2 oranges, we have 4 possible outcomes. Neither orange could go bad. The probability of that is 81%. Both oranges could go bad. The probability of that is 1%. And only one orange could go bad. The probability of that is 9%, but there's 2 ways that could happen. So in total, the probability of one orange going bad is 18%. 81% plus 1% plus 9% plus 9% gives you 100%. That's all the possible outcomes. To calculate probabilities using the binomial distribution in Excel, we use the function binomdist. This function takes 4 arguments. The first is the number of successes you seek. The second is the number of trials. The third is the probability of a single success. And the fourth argument is either the word true or false. If you use the word false, the binom.dist function gives you the probability of exactly a certain number of successes occurring. If you use the word true, binom.dist gives you the probability of the number of successes or fewer occurring. For example, suppose that on average a car salesman sees 200 customers per month and sells 20 vehicles a month. To keep his job, the salesman must sell more than 10 cars per month. Given this information, what's the probability that the salesman will sell more than 10 cars this month? This is a binomial distribution. Success is selling a car. We have 200 trials. That's the 200 customers that will come in this month. We're looking for more than 10 successes. That's more than 10 car sales this month. On average, in a given month, this salesman sees 200 customers and sells 20 cars. So the probability of a single success, the probability of selling a car to a customer, is 20 divided by 200, or 10%. So using the binom.dist function, we enter the arguments 10 for the number of successes, 200 for the number of trials, 0.1 for the probability of a single success, and the word true. The function returns 0.008. This is the probability of the salesman selling 10 or fewer cars this month. So the probability of the salesman selling more than 10 cars is 1 minus 0.008, or 99.2%. Now suppose the manager offers a $5,000 bonus if the salesman can sell 30 or more cars in a month. Based on this information, what is the probability that the salesman will sell 30 or more cars this month? Using the binom.dist function, we enter 29 for the number of successes, 200 for the number of trials, 0.1 for the probability of a single success, and the word true. The function returns 0.984. This is the probability of the salesman selling 29 or fewer cars in a month. So the probability of the salesman selling 30 or more cars is 1 minus this, or 1.6%. Now, to keep his job, the salesman must sell more than 10 cars per month, but suppose the economy has slowed so that this month the salesman expects that only 150 customers will come in. What's the probability that he will sell more than 10 cars this month? Using the binom.dist function, we enter 10 for the number of successes, 150 for the number of trials, the probability of a single success is 0.1, and we use the word true. The function returns a probability of 10.6%. This is the probability that the salesman will sell 10 or fewer cars this month. So the probability that the salesman will sell more than 10 cars this month is 1 minus this, or 89.4%.